Hi everyone, I'm Houkon. Thank you for Malik's presentation. I'm also working on blades, but digitally. I'm from TU Berlin. To keep everyone on the same page, let me first introduce some basic concepts. Maybe most of you have known. I will introduce them briefly. So gas turbine is a machine which burns gas-like fuel to generate mechanical drive, which is the rotation of the blades at the left side of the gas turbine. As you can see at the bottom figure, the blades here are loud and they are very expensive, which means we need a regular maintenance and repair for these blades. And this process is often referred as maintenance, repair, and operation process, in short, MRO. And our goal is to convert traditional MRO process, which basically is the engineers check the manual book manually and then decide what operation should they take. And what we want to do is to have automatic and data-driven support for this MRO process. Our system is called Smart Export, and we got real data from Siemens. As you can see, the data looks like we have measurement for different blades, and at the same time, we get a repair decision from engineers, what they have done, decided for such blades. For example, one is scrap, which means we don't need the blades anymore, so we just destroy it. And the rework means we need additional repairing operation so that the blades could be used later. And used as is means the blade is good to put back for a customer to use. However, this data, as you can see, is not balanced, and we have only limited size. Therefore, we decided to use Design tree in our system because it's easy to interpret, which means the engineers can trust our model when they use our system, because they understand what the system does behind. On the other hand, we use Design tree is because we only have limited size data, and Design tree performs well because it learns efficiently from limited size data. Another critical decision we have made is that we reserve the concern of underestimation. The underestimation is a situation that the reality of a blade is scrap, for example, but we predict as used as is, when we put back this blade back to the customer, it will be a big trouble, as you can see here, that it could lead to complete damage to customers' gas turbine, which is a disaster. Therefore, we prefer overestimation. If 100% accuracy is not available, which is the reality for us. And an important metric we introduce here is underestimation ratio to resolve this problem, which is the number of underestimated prediction divided by total predictions. To put it simple, this is the ratio of predicting better than reality. And as the issue we have discussed before, therefore we introduce conservative prediction, which is we consider the severity level rank into the prediction decision. And we predict according to the order if we have strong enough belief or possibility that a severe level could appear. For example, here, we would rather prefer or predict scrap, though it only has a 43% chance. But because of this preference, and it turns out, as you can see in this table, our results show that our conserved prediction can improve underestimation ratio from 8% to 5% at only cost of 0.5% of F1 score, which is a combination of accuracy and precision. So Smart Export can improve the prediction safety at low cost. apart from that, we design our architecture in a decoupled way, such that in the experiments you can see this is the latency, which means how quick our Smart Export can process requests, and with more deployment of our system, we can flexibly adapt to changing demand. Therefore, we encourage you to think about to use Smart Export to improve ML process. Because as you can see here, Smart Export can automatically and provide data-driven decision support. And it can resolve prediction safety concern as well. Last but not least, it's flexible with changing demands. And this is our team, and this is my contact. Thank you for your attention.